Hello, everyone, and welcome to the session. OTV, Overlay Transport Virtualization. This technology has been there for quite some time now. A lot of enterprise clients have already deployed this technology successfully in the network. However, there are still a good number of people who ask questions how OTV works, how exactly the packet flow looks like, and a lot of times we see that people struggle to troubleshoot if anything breaks. The whole idea of this package of this video is to make you comfortable with the OTV end-to-end, starting from the basic workflow, the configuration, and finally some of the useful troubleshooting tips. I'm going to break down the whole package into a few videos, and the agenda for the complete package looks like this. At the beginning, we will take a look at the overview of OTV, the basic packet flow. Then we will start taking a look at the configuration of OTV Underlay. Even though the OTV Underlay could be less significant for most of the clients because they might be using a third-party provider who is going to give you the connections. Could be internet, it could be a dark fiber, anything. However, it is still important to know the underlay when you are trying to troubleshoot something in the OTV. Then you look at the OTV overlay. We have two different modes, multicast and unicast. We look at FHRP filtering, which is needed to make sure that your inter-VLAN communications across the two data centers are working fine. Then we will take a look at summary of some of the verification tools, CLIs, commands. We will uh, we will go through some of the tips of troubleshooting. And finally, we will take a look at the packet tracer tool, which is part of your OTV troubleshooting, which is available on XC platforms. We will explore that also a bit. Going forward, what is OTV and why OTV? So this is basically a Ethernet over IP tunnel where you have two data centers and you are trying to extend your layer 2 domain across the two data centers over the IP network. Let's say that you have a host which is connected to data center 1. This is, let's say, DC1. And then you have some kind of IP network in between. It could be anything. It could be MPLS, it could be internet, it could be your dark fiber, it could be anything. And then on the other side, you have DC2. Okay, this is DC2. And then you have another host connected here. If this host is in VLAN 10 and this host is also in VLAN 10 and they're trying to talk to each other, then generally in the traditional IP networking, you cannot make it work because you have an IP network in between. However, in this overlay technology, using this overlay technology, we are going to extend our layer 2 fabric across the DCI interconnect, across the IP network to the other data centers. If you have applications like vMotion, where you need to move your servers from one physical location to other physical location, uh, you do not want to change the IP address. You do not want to change the VLAN. You do not want to rephrase the ARP cache. You want to keep everything same. So this network is going to enable you uh, to run those kind of applications which can seamlessly move across two different data centers, even though they're miles apart. So if you have one application which is in San Francisco and you have one data center which is in San Francisco and you have another data center which is in New York, you can move the applications between San Francisco and the New York data centers without even worrying about changing the IP address or anything. It will look like the same IP address, the same ARP cache, the same VLAN. The only thing is you can just move them in different locations, right? That's what OTV is going to enable you to do that. And that's what we mean by extending the layer 2 domain as well. It will look like a flat layer 2 network you have across the IP network. Site to site tunnel. Uh, as you see in the diagram, this OTV is basically going to be formed between these two edge devices in the two sites. It is a little different from what we have in VXLAN and BGP VPN, where you have the tunnels formed between the VTEPs, which could be all intra-sites. In this case of OTV, you do not have any tunnel intra-site, but it's between the sites, it's inter-sites. And also, if you compare this with GRE, so in the GRE, you have the destination, which is hard-coded. But you will see in the OTV, when you look at the configuration part of it, it can be dynamic when you are using the multicast mode. Transport agnostic and hardware accelerated. OTV can carry almost any kind of traffic, almost any kind of traffic. So and also uh, it can be transported over any network. It could be a MPLS, it could be a dark fiber, it could be a simple internet. You can transport OTV packets over any network. That's why it is called transport agnostic. If you are using the OTV in the multicast mode, then your underlying network needs to support the multicast. That's the only challenging part. And if you use internet, then your ISP is not going to support multicast. It's not going to route the multicast packets for you. So you cannot run OTV in multicast mode in those scenarios. However, there is a workaround for that, which is the unicast mode. But technically, you can run OTV on any kind of transport. Hardware accelerated, basically OTV can be uh, programmed in the hardware, the OTV routes, and it can be forward. The packets can be forwarded in the hardware, which we do on Nexus 7K platforms. We also do it on ASR 1K platforms as well. And also we can use the CSR 1K, which is the cloud service router for Cisco. Separation of STP, ARP, and unknown flooding. OTV edge devices, it doesn't forward the STP packets across the sites, which means even though these two clients, as you see in this diagram, even though they are in VLAN 10, even though these two guys can exchange the ARP packets, the STP domain in site 1 and the STP domain for VLAN 10 in site 2, they are actually different. So the root bridge of VLAN 10 on site 1 would be local to that site, and the root bridge for site 2 in data center 2 would be local to that site. The reason we are doing it, because if any STP convergence happens, or if anything bad happens in one data center, we don't want other data centers to be impacted because of that. OTV by default, it suppresses ARP packets because it also maintains a local cache of the ARP based on the OTV routes. For example, if this client A here, it is trying to send ARP packet for client B, then this ARP packet actually will be reaching this client B. And then when the response comes back, then of course the client A is going to learn the ARP entry for client B, right? It will learn the IP to MAC mapping of the client B. What happens at the same time, this OTV edge device is also going to create an entry in its ARP cache, OTV ARP cache for this client B. Any other clients from the same data center, if they are trying to reach client B and they are trying to resolve the ARP for client B, in that case, the OTV edge device is not going to forward those ARP packets over the tunnel again. In that case, it will simply send a reply to that particular client, say, hey, you know what? This is the IP to MAC mapping for client B because I already have it in my cache. That reduces the flooding, that reduces the bump traffic, which is your broadcast, unknown unicast, and multicast flooding over the overlay network. Multipath and multipoint. You can have more than one edge device in a given site. Say, for example, in this site A, we are adding one more edge device, right? This is edge device 1, and this is edge device 2. These two edge devices, they can load balance the traffic for different VLANs. Odd VLANs can go to one edge device, and the even VLANs can go to the other edge device. So basically, this is a load balanced way between the two edge devices for the different set of VLANs. If VLAN 11, this OTV edge device 1 is active for, then this OTV edge device will be inactive for that. Similarly, for VLAN 22, which is an even VLAN, if the edge device 2 is active for that, then the other edge device 1 will be inactive for that. What we achieve by that is we can prevent loop. And this is where it is a little different from your Ethernet over MPLS network, where you basically transport your STP packets as well. And if you have a backdoor network, then it can cause a loop unless you are blocking one of the packets, one of the link in the STP. But in case of OTV, since you are not forwarding your STP packets, because you don't need that. In this case, the edge devices, what you have, this is basically one of them is going to be active, other is going to be on the standby. So even if there is no spanning tree, it is still going to prevent the loop using that. Multipoint is OTV site tunnels, not necessarily they have to be point to point. So you can have actually more than two sites connected to the same IP network. I mean, connected to any kind of IP network, as long as they have the reachability, the IP reachability, you are fine. You can just, it's kind of a plug and play. So let's say you already have these two tunnels working together, these two data center sites, and you have one more new site here. As long as you have IP connectivity to site 1 and site 2, you can join the same OTV tunnel with you. So this is point to multipoint. Compare OTV with VXLAN, BGP VPN, and traditional L2 VPN. We talked about this in a little already. In traditional L2 VPN, you do not forward your STP packets. But here in traditional L2 VPN, you do forward the STP packets, but here in OTV, you do not. And that's the reason you have one active and one standby device for each VLAN in the site, right? If you compare with VXLAN BGP VPN, then it is basically a VTEP to VTEP tunnel where it is intra-site, but OTV is always a site-to-site tunnel. You do not have any tunnel inside the site. The other advantage of OTV is if you are using a layer 2 VPN service or VPLS service, then you need to go to your service provider asking them to, hey, can you provide me a L2 bridging service between two of the sites or between 3-4 sites of mine? But in this case, you have it completely in your control. It is in the control of the client. You do not need to go to your service provider asking to do anything. As long as you have IP connectivity, you are good. You can build your tunnel, you can build your overlay. And of course, one point we need to keep in mind, if your transport underlay doesn't support multicast, then you cannot run OTV in the multicast mode. However, it's not a problem anymore because we can work around that completely by using the unicast mode of it. We will take a look at that in detail down the line. All right. Let's take a look at the OTV Basic Workflow. The OTV control plane is built by ISIS. ISIS packets will be sent to the multicast address. Now, when you are using the OTV in the multicast mode, then OTV encapsulates the ISIS packet inside another multicast packet, which is the OTV control group. We will talk about this in the other slides. And that way it can discover the other tunnels, other tunnel endpoints. It can discover the other sites. To begin with, when you configure the OTV in the multicast mode, you do not hardcode the destination IP like what you do for GRE. Using the multicast, it basically discovers the tunneling points dynamically. Once the tunnels are formed, once the ISIS routes are advertised, like basically your MAC addresses are here, your like your prefixes, and the MAC addresses are all advertised using the ISIS protocol. So when you have this converged, then in the data plane, when the traffic needs to flow from one data center to another data center, then it can simply unicast, it can simply encapsulate that packet in the unicast IP header with the source IP of the source edge node and the destination IP as the edge device IP address of the destination site. The MAC addresses are learned over ISIS, that's what we talked about. And then traffic across the site can be encapsulated in two different ways. You can encapsulate with the Ethernet packet over MPLS, over GRE, over IP, and also you can do it with UDP as well over IP. So the idea of using MPLS and UDP here is, if the traffic is for a specific VLAN, you don't want the VLANs, all traffics to be merged or categorized in a same pipe. You want to segment the traffic for VLAN for different VLANs. So in the MPLS, you basically what OTV does at the backend is it creates a specific label for different VLANs. So that way it can segment between the different VLANs. Similarly for UDP, there is a special field what it uses to segment the traffic for the different VLANs. But you don't need to worry about anything, as OTV does everything at the backend itself. Uh, uh, Let it be ISIS, let it be the MPLS encapsulation or the UDP encapsulation. It's all done behind the scene by the OTV itself. Let's take a look at OTV terminology. Edge device. The diagram what we have drawn earlier, if we take a look at that example again, let's say these two are my uh, ASR1K devices, which are going to be my OTV tunnel endpoints in this site A, and you have an IP network in between. Let's say this is your IP network, and similarly you have two more devices on the other side. In fact, you can have another site here like this. So this is site 1. Let's say this is site number 2, and this is your site number 3. So all these devices, what you see here, these all are edge devices. Next, authoritative edge device. As we talked about in the previous slide, not both the devices, edge devices, are going to be forwarding the traffic for same VLAN. If one device is going to be forwarding traffic for the odd VLANs, then the other edge device is going to forward the traffic for the even VLANs. So whichever device is the active forwarder for a certain VLANs, they are called authoritative edge device. In our example, if let's say all the odd VLANs are hashed, or this particular edge device is going to be the authoritative edge device for all the odd VLANs 11, 13, 15, like that. And all the even VLANs are basically being forwarded by this edge node here. Let's say this is 18, 20, 22. So for all these odd VLANs, this guy is the edge device, authoritative edge device. And for all the even VLANs, this node here is the authoritative edge device. Extend VLANs. This is nothing but all the VLANs what you want to bridge over the overlay. In our example, if 11, 13, 15, 10, 20, 22, if we want to extend the layer 2 for all these VLANs, we call them extended VLANs. OTV site VLAN. Apart from this extended VLANs, we should also have a site VLAN for each site. That VLAN will be used to make these two OTV edge devices talk to each other. Using that VLAN, these two edge devices can decide that, okay, these are the VLANs I'm going to take care of, and you're going to take care of the other VLANs. Also, if one of these node loses the uplink the join link, which is the tunnel uplink, then it needs to inform the other edge device, hey, I don't have any reachability to the data center interconnect anymore, so you have to take over the rules for all the VLANs, and this all communications are actually done in this site VLAN. So this is very important. Next is OTV Site Identifier. Each site in the OTV fabric needs to have a unique identifier. For site 1, maybe the number could be 0x1. You can give any number you want. For site 2, it could be 0x2. And for site 3, it could be 0x3. So whatever number you give it to them, but they have to be unique and they should not be duplicated across sites. Next is overlay interface. One more thing I forgot to mention. For the OTV site identifier, if you have two edge nodes in the same site, these two edge nodes, they must need to agree or they must need to have the same site identifier. Because if the OTV site identifiers on the two edge nodes are same, they won't form the bridging, they won't form the tunnel. And if they are different, then basically they are going to form the tunnel. So you have to be careful on that part. The overlay interface is basically the logical representation of the OTV interface. This is very similar to interface NV1, like what you use in VXLAN, BGP, VPN, or maybe interface tunnel 0, interface tunnel 1, what you use in GRE. So in this case, it is interface overlay. OTV join interface. OTV join interface is the interface which your edge device uses to talk to the data center interconnect. In this example, this edge device, let's say this is the interface Ethernet 0x0. And for this edge device, let's say this is 0x1. So for this node here, 0x0 is going to be the join interface. And for this node, it should be 0x1, which will be the join interface. Now, there are certain restrictions on different platforms. You cannot configure a loopback as a join interface. You might not be able to configure a VLAN interface as a join interface. So there are certain restrictions, but most cases you are, of course, allowed to configure the physical interface, the layer 3 interface as a join interface, or maybe a port channel. Control group and data group. This is something which is used in the OTV multicast mode. If you have, as we talked about, right, whenever the ISIS packets need to be sent out by edge device to discover the other tunnel endpoints, it will be encapsulated within another multicast group so that everyone, all the sites, they all are listening to one particular group. And whenever this device is going to send the ISIS hello packet, then it should be delivered to those sites. It should be delivered to all the all those sites, all those edge devices. So for that, they all need to listen to one particular group, and that is what is called as control group. We can define that when we configure it. We will take a look at that in detail, but this is something it's manually coded. And then comes to the data group. If you have in the multicast mode again, if you have multicast traffic that you need to encapsulate within another multicast packet, then you can use the data group IP address, which you can define again on your overlay interface. You will pick the IP from that range and you will encapsulate your actual multicast packet into with that IP address, and it will be recirculated to all the other sites who are interested to listen to that group. Or if the same can be used for bump traffic as well, for broadcast, unknown unicast, and multicast packet as well. Adjacency server. Now, in the unicast mode of operation, we cannot use the multicast control group and data group. In that case, what we do is one of this node here in any of the site, we can configure that as adjacency server, and the IP address, the join interface IP address of that particular node, we configure on all the other site devices as an adjacency server. Now, when you define the adjacency server, it basically makes it look like a DMVPN tunnel where you talk to that server to know who all the other tunneling points are, because everyone is going to reach to this guy, right? So this guy, the who is the adjacency server, he knows who all are the tunneling points. So that basically helps the each edge device to know about all the tunneling points. And when they know about it, then they can basically encapsulate all the packets in a unicast IP for the distance or with the join IP address of those respective edge devices, and they can send the packet to them, right? So this is basically just to work around the problem which we can encounter while doing the multicast mode of operations, because most of your underlay networks like internet service provider, they might not support MPLS. I'm sorry, they might not support multicast. So that's pretty much it for this session today. In the next session, we're going to talk about OTV building underlay. Then we will look into OTV multicast configuration. We will look at OTV unicast configuration, which is most popular. After that, we will take a look at the FHRP filtering as well. And then, of course, we will take a look at some of the troubleshooting tips. Thanks for watching. See you soon. Take care. Bye bye.